Okay, we are now going to get into a little bit more detail on one very specific example of a finite state machine, and in this case I am going to use an example of something called a traffic light control, right. I will define exactly what the problem statement is and why we probably need some kind of a finite state machine controller, how to go about implementing it, actually walk through the entire Verilog code for it, and look at a simulation of how the system works. So, the problem statement is something like this. We have an intersection of two different roads, right. We are calling this the north-south road and the east-west road, okay. And in some sense what we have is that the main road goes from north to south, right, and the side road goes from east to west, okay, and the priority therefore is generally for the main road, right. We also have a pedestrian crossing button, right. So, what happens over there is we have some kind of a button that can be pressed at each of these intersections. So, for example, at this point over here I have a button. Let us say that I want to cross the road from south to north or north to south. I have this button that I can press that basically asks for this walk sign to be activated, okay. Now, think about it, when do I need that? Let us say that my north-south signal was already green. It means that no traffic can go from east to west, which means that whenever north-south is active, in general it should be safe for the walk north-south to be equal to green, right, or to be active. But when you have an active green on north-south, I should definitely not have a walk signal allowing people to cross from east to west or west to east, okay. Similarly, if the east-west traffic is active, my walk north-south should not be active, and vice versa. Another thing that I can be clear about is I cannot have green over here for north-south as well as east-west at the same time. So, in other words, it looks already that this problem is not a trivial problem to solve. There are some kind of conditions under which I need to implement it, but it also looks like it is fairly structured, right. So, let us try and define this problem in a little bit more detail and then go through and see how an implementation would look, right. One of the other things that we have, as in most cases you would know that traffic lights actually have some kind of timing associated with them, right. Of course, in a lot of traffic signals there is actually a police personnel over there who is involved in controlling the signal and deciding when it transitions from green to yellow to red and then back to green and so on, right, and in what order the rotation of the signals happens. But what we are talking about over here is, can we do something automated, which also means that apart from having all of these rules like not having simultaneous greens and so on, we would also like to associate a certain timing with each of these signals. In other words, north-south should be maybe for 10 seconds, after which it basically transitions, right, and then the east-west turns on for a certain amount of time, once again transitions back, north-south turns on and so on. Now, while the transition is happening, we also want to make sure that it goes through a phase of yellow, and what that means is I shouldn't go directly from green on north-south to green on east-west. I need to give everybody time to sort of stop and then activate. So, what will happen is I initially have a north-south green, I then go to a north-south yellow and then red. At that point I actually have red on north-south and red on east-west. So, no traffic is supposed to go in any direction, but once that is done I can then turn on the east-west green light and then proceed. So, we have a number of complicated sequence of operations that we can sort of envision over here, right. Let us try and make it systematic and also try to put together some kind of safety requirements and how we will handle different potential faults in the system, or inputs that are not matching what we expect. What I have shown over here is are two things. One is a state diagram corresponding to what I think is a valid behavior for this entire system, and also a sort of potential sequence of operations that we have. Let us start by looking at this potential sequence of operations and then understand why the state diagram makes sense for the kind of functionality that we are looking at, right. Now, you can sort of ignore this clock signal out here, I am just using it to sort of synchronize values. These numbers how many clock cycles each of these things are there are just, they don't really relate to the number of clock cycles over here or to what is implemented, right. They are more sort of illustrative in terms of how the transitions happen. First things first, let us assume that by default we are in the north-south green signal, right. As we know, north-south is the main road, therefore it is green. Now what happens over here is, let us say that a pedestrian who wants to cross from east to west, right, presses the signal asking for the north-south signal to change. Now what happens is, that signal gets picked up over here, but it then takes a little bit of time, right. In this case maybe one cycle, but as we will see later it might even be more than one cycle before the system starts to respond. Now what does that mean? First things first, it is not straight away going to turn the signal red, because that could be very alarming to people who are actually driving from north to south or along the north-south road. What it needs to do is transition to yellow, give it a certain amount of time in yellow, and then transition to red, okay. And during this entire time the east-west lights are basically red, right. The other thing you might notice is, while the north-south main road traffic is green, the north-south walk light is also green, right. And when the north-south traffic light goes yellow, at the same time the walk light also goes to yellow, okay. This is a design decision. We might choose that, the north-south light is actually only green when there is somebody trying to walk. Those are again choices that you can make. But the important thing is, the east-west lights remain red until this point where the current state goes into R1, right. After that the east-west light becomes green, the walk signal also becomes green. The point is, it was actually only the person who asked for the east-west lights to become green who wanted to walk, due to which the east-west lights have become green, right. But the interesting thing is, once the east-west lights become green, it basically goes into a mode where it waits, but after a certain timeout, right, let us say that the person has finished crossing and so on, in any case even without an additional pedestrian in the north-south direction, the east-west times out, goes to yellow, goes to all red, right. This is now the R2 is also an all red state, all signals red, and then finally goes back to the default, which is north-south green. By what we have already discussed, most likely this north-south green would also have a certain timeout, after which it would switch back to north-south yellow and R1 and then EWG, even if there are no pedestrians anywhere in the picture. What is important is, when the pedestrian was there, it sort of responded fairly quickly, okay. Now you might also notice that there is an R1 state and an R2 state. It seems like they should be the same, they are not, and the reason why they are not is, after R1 I need to go into EWG, that is the east-west becomes green, whereas after R2 I need to go into north-south green. So they are primarily, and there are no other inputs in the system, so the best way to encode the fact that my next state should be east-west green is directly in the state transitions themselves. That is exactly what we see here, right. I start out in north-south green. If there is a timeout or the pedestrian east-west has been pressed, I go to the yellow state, wait for a certain amount of time which is indicated by the yellow done signal, go to an all red state. Notice that over here I am just calling it all red, whereas over here I had to give it a unique name R1. After all red I wait for red done, I go to east-west green. This also allows my lights east-west to become green. I have not indicated the outputs over here, but that can be seen in this part of the diagram. The east-west waits for a certain timeout, or if there is a pedestrian trying to cross from north to south or south to north, right. In either of those cases it goes into the east-west yellow, waits for yellow done, goes to an all red. This all red and this all red are different states. Why? Because the next state is different. But in either case what actually happens is, after the red done, I now go to a north-south green, in this case an east-west green, okay. So this state diagram seems to capture most of the functionality that we have talked about. Now let us see about implementing it. So there are several design requirements that we need to keep in mind over here, right. In general our system looks something like this. First thing, we need to know what are our inputs. We have a clock and we have a reset, right. The reset is just to bring the controller to a known state. The clock is used to basically run counters and think of things like timeouts. How does a timeout get implemented? There are also buttons that indicate when a person has pressed the either north south or east west walk signs, right? And there is another signal which is a generated signal internally, which says whether the specific timer that you are currently in has expired or not. All of these inputs go into our controller FSM and generate certain outputs. It also has one more sort of separate piece of logic out here, which technically is part of the FSM, but the reason I am counting this as a separate timer out here is because if you go by the strict definition of an FSM, the total number of states in the FSM is the total number of registers present in the FSM and essentially determined by 2 power the number of registers that we have. Now this counter on the other hand is not really contributing to the states in the FSM. It just allows us to measure a timeout. So rather than saying that the number of states expands out into ns green underscore 1, ns green underscore 2 and ns green underscore 3 up to ns green underscore 1000, I can just say I have an ns green in which I have a counter going from 0 up to 1000, right. So the timer is sort of a secondary input to my finite state machine, as we will see in the code shortly. It's a very useful and powerful construct over there, but we don't necessarily need to think of it as part of the FSM. It doesn't add states to the FSM. What does the FSM do? It generates of course the next state logic, and it also generates the outputs, north south lights, east west lights and the pedestrian crossing signals. So there are a few design requirements that we have. We have already specified what our inputs and outputs are. We need to give certain priorities, right. The main road north south has highest priority. If there is a pedestrian trying to walk along the main road, or rather if there is traffic on the main road, then they get priority. And we can also have something which says there must be a minimum green time. In other words, let us say that north south has just turned green, right. What if a pedestrian is again immediately comes in there and presses the button saying I want to cross from east to west? It does not matter. Usually they need to wait so that there is a certain guaranteed amount of time for north south green. Now as you will see later, the present implementation that I have got does not actually take that into account, okay, but it's easy to add, right. So the way that you should think about the present logic is more as a illustrative piece of code rather than the definitive correct way of writing the code or the only way of writing the code. There should also be maximum wait times for the side road, basically saying that you time out after a certain while, and even if there is no real traffic or some kind of a pedestrian signal, the north south should stop and east west should get activated. There are certain safety considerations. The yellow light timing must be fixed. This is just from the point of view of vehicle safety. In general, if a vehicle is speeding towards a signal, it may not be able to stop abruptly if you transition from green to red. That's why the yellow light exists, right. It basically says slow down. If you have not yet reached the signal and you can safely stop before you reach it, you should try, right? And if you feel that you are so close to the signal that you cannot safely stop your vehicle and you will end up overshooting and causing problems, then you may go through. Unfortunately, in a lot of scenarios we tend to take the approach that the yellow is sort of meant for us to speed up and try to push through the signal. That's a very dangerous way of looking at driving. Ideally what we should do is make a judgment call and say, okay, I am far enough away, I should be able to stop comfortably, let's let this signal go and take the next green. Now we also want to enforce an all red period during transitions. This is just to make sure that everything comes to a known state. You don't want to abruptly transition from yellow to green and yellow to red in one direction and from red to green in the other direction at the same time. You want to make sure that there is a slight overlap when both sides are not allowed to move, right. That's more of a safety consideration. You might choose to make that a relatively small amount of time, but it's always better to have that as an option. Now how do we handle pedestrians? The buttons will trigger a light change request. The amount of time for the walk signal will be fixed, it must be fixed, and also we must have this thing where we actually finish the vehicle yellow before turning on the walk signal. Same as before, right. I mean, we want to make sure that while there is a possibility of traffic going through, we do not accidentally ask pedestrians to start walking. There are a few other considerations. All of these are from the point of view of how the actual functionality works. There are also scenarios where we want to make sure of fault tolerance, right? The safe state on reset should be an all red state, right? We do not, as soon as the system switches on, or let's say there can even be strange scenarios like, for example, you have a storm and lightning hits the controller circuitry box, right, and basically causes the entire thing to all the states of the system to get randomized, right? Maybe it doesn't destroy the circuit, it just sort of gets them to randomize. You might in fact have noticed this, that in certain kinds of scenarios in storms, traffic lights very often go into a blinking yellow kind of mode, right? And there is a reason for that. That is essentially considered a reasonably safe default. An even safer default would actually be an all red mode where nobody is allowed to travel. But if there is actually a problem with the system and the system is sort of shut down and hasn't come up properly, maybe a blinking yellow is a safer one. What blinking yellow means is there is a problem, these lights are not operational, you need to exercise caution, slow down when you reach the signal, and if there is no other traffic, you are free to go. Okay. So, what choice you make is again left to you as the designer, well, you as well as whoever is designing the system, right, not you as a circuit designer. Watchdog timers, these are critical safety components over here, right, because traffic light control actually has life or death consequences if not implemented properly. You need to make sure that the system does not get stuck in arbitrary states. So, watchdog timers, things that basically just make sure that your system is transitioning out of any stuck states, are required in general in these things. Among other things, you might also have a scenario where buttons can get stuck. So, what do you do in such a scenario? Do you actually somehow detect that the button has got stuck and after a while maybe just override it, or do you keep going into a loop where you get back into the pedestrian wants to cross, the pedestrian wants to cross? That is again where the minimum green times help, which say that okay, even if the button gets stuck, it will at least ensure that there is a certain amount of green time that is guaranteed in each direction. Not the perfect solution, but at least a safe one.